Hi there, today I want to go through something a little bit different. It's tangentially related to the video and audio hardware I've been working on, but today I want to go through designing a simple CPU using TTL through-hole components. This started because one of my Twitter friends commented that they really want to do something with electronics, but they don't really know where to start. I know they are an accomplished software engineer, so I'm trying to approach this from the point of view of coming up with a design for a simple piece of code to execute, and then designing the hardware around that code. So using code in this way, I'm able to describe some simple behavior that I want to see, and then I can use this to validate the hardware TTL design when it executes this code. So the type of code, the code that I've chosen for this is basically a simple Fibonacci sequence, and the test pseudocode that I want to execute against this design is here. So what I'm doing is that I'm describing in pseudocode what I want the steps to do. So this writes an address register with the initial value of 13 in decimal. So I want to start, for example, writing the Fibonacci sequence to some memory at address 13. I could start it at the beginning of memory, but I want to test being able to write an arbitrary value into the address register, so I've chosen 13. I want to write 0 into register A, and I want to write 1 into register B. When I say write, it's basically the same as loading a register with a value, but I want it to have the same kind of terminology for write, whether it's for a register or for if it's writing RAM. So then we have the start of a loop. The label for the loop is .loop. And by convention, it's usually on the left-hand side, and it's usually not indented. This is just pseudocode. And then I have write RAM. Now, RAM writes always use the value of the memory address, which is in the ADDR register. However, in this example, in this simple CPU, it's actually capable of writing more than one destination in the same instruction. And in this case, I want to write the result also into register C. And the result is actually the result of an operation adding registers A and B together. Now, registers A and B and address and also register C and also the program counter in this example are going to be a simple 8 bits in size. I'm not going to make it have larger registers than that because it helps to keep the design small and easy to understand, or easier to understand when looking at it in the schematic. I'm then going to transfer over from register B into writing into register A the contents of register B. And then I'm going to move whatever is in C into B, because that's what the Fibonacci sequence is. You're taking two numbers, shifting them over and adding them, or adding them together and then shifting them over and then iterating on this. The next instruction in this pseudocode is to increase the address register by 2. Here. Now this is with an immediate value of 2 in decimal, the same as the immediate value here for the address register and the immediate value here for the A and B registers. Now, this next line actually does a comparison and conditional jump. And it looks quite complex, but it's actually not really that complex. So, as the comment says, this add is used as a comparison. The result is not stored, and it behaves like a conditional branch or jump. So, taking the value that is in C, register C, which was written from the addition of registers A and B, basically temporarily stored. Okay. Taking the result of the add and subtracting 89 from this basically does a test with 89. If you take 89 and you subtract 89, if you end up with 0, then I want the code to fall through to the next line. If it's not 0, then I want to write the program counter basically with the immediate value of loop, which is the address of loop, which tells the program counter to go back to here. So hopefully what this code should do is that it should execute this loop until the value 89 is written into memory, or thereabouts. That's what the code should do. So, and then at the last line here is that the last line of the code should loop around this end statement here in an infinite loop, basically writing the program counter with the address of the end label in this pseudocode. So looking at this code, analyzing the pseudocode, there are various functions to the CPU. So the functions of the CPU can be broken down into these parts. There is a program code which also contains immediate values, which can be in ROM. There's program RAM, used to store the results calculation. There is an address register, which is used to address the contents of the RAM, the memory. And there are 3 registers, A, B, and C, which are general purpose storage registers. So I can load and store those values. And there is a PC register as well, which is the program counter. Now the program counter also is able to have values written to it, but also it must increment. And it's useful if it can self-increment. So it's probably going to use some counters rather than just 8-bit latches. A write instruction, which writes a value into a destination register or memory from a source immediate value or the result of the add instruction. So basically we want to have the notion of an internal data bus, a data value bus. The write instruction can also write multiple destinations from the same single source value. An add instruction, which is used to add registers, or a register and immediate value. So we know that we're going to have to choose the 2 inputs for the add instruction. Now, in CPU terminology, this is usually called the ALU, the arithmetic and logic unit, but basically we're just having an add at this point, but the add has a couple of different choices for its 2 inputs for the add. And lastly, there is a conditional if not 0 modifier to any instruction, basically, which allows the write instruction to execute if the current result is not 0. So when we're looking at the potential design for the parts of the CPU, we have 4 general purpose registers with read and write. We have 1 PC register with write and increment. We have an ALU, which is just an add operation. There are 8 sources of data that can be used for a write. The immediate value from the ROM at the program counter, values from RAM at the address, 5 registers, and the result of the ALU. There are 6 parallel write destinations, so 5 registers and RAM. So we're going to need at least 5 signals. And we have the conditional if not 0 test and write logic. This needs to also take into account the reset signal. So generally speaking, we want to have a reset signal And the reason why it's underscore reset is by convention. This means that it's a reset on 0, on a reset on the low value. Digital electronics, of course, being you only have 0 or 1 value, generally speaking. So we want to reset the internal CPU state to known values. This means, say, for example, clearing the program counter to 0, clearing all of the internal registers to 0, and so on and so forth. The output clear will also clear the instruction latches coming from the program memory. Now, this is going to be quite important because we're going to be using ROMs for the program memory, and because we're going to be incrementing the address that's fed into those ROMs, generally speaking, the output from ROMs is not clean. It's not always stable. This means that we need to wait for a period of time before the output from the ROMs becomes stable and valid. So we'll be using at least one row of output latches to latch the output from the ROMs to make sure that we have access to nice stable values. Now, we can use a truth table solving tool to help us calculate the logic that we actually want to use when we want to try and solve this truth table that we can see below. And also note that the last significant and most significant bits for the clear output and the ordering. Okay, so by convention we have A, B, and C because we have reset, the OR IData, and the if not 0 signals, resulting in what we want to see from the clear. So say, for example, on low, on reset low, we always want to have an output 0 for the instruction memory clear. And if reset is high, then we want to ignore reset. And then what we want to do is that we want to look at the result of these two, B and C, which is the OR IData and the if not 0 signal. So OR IData is basically going to be the result of all of the bits of whatever data we're looking at currently, or together. So if all of the bits are 0, then OR IData signal will be 0. And if any bits are in the value we're looking at are set, if any bits or all of the bits or some of them are set, then we're going to be seeing a 1. And with the if not 0 signal, this is going to be 0 or 1. Now, if it's 1, that means the pseudocode has the if not 0 modifier set on the instruction. So if we have if not 0 set to be 1, then we want to have a look at the bits. And say, for example, if the if not 0 instruction modifier is set and used, but what we're looking at in terms of the internal data bus is all 0, then what we want to do is that we want to signal to the CPU that we want to ignore this instruction. We want to clear the instruction, basically clear all of the bits in the instruction to 0, so that this current instruction will not execute anything at all, and the program counter will then just tick, and the program counter will increment, and we will fetch the next state of the instruction. Okay, so we'll ignore it, and then basically what that means is that the instruction will fall through to the next instruction rather than executing the write. And if the if not 0 modifier is clear, then of course we ignore it and we don't clear. And of course, if any of the bits in the current data are set, signified by 1 here, and if we're doing if not 0, then we also do not want to clear. So if we want to use the truth table solver, what we can do is that we can go there straight away, and I'll show you what it looks like. So this is the truth table solver. What I want to do is I want to just give it all of the values, because I want to give it all of the values for the expected output. Bearing in mind that, look, this is counting up in binary, so 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1. It's the least significant bit here and the most significant bit there. And this is just the way that this orders it. This basically means that we don't have to give it the whole truth table, we just give it the expected output bits, and it knows that the rest of the expected bits and stuff in the truth table follow this expected pattern here, so we only need to give it this. So it's 0, 0, 0, 0, 4 zeros, and then 1, 0, 1, 1. And because I've used this before, the values are here already, but basically 4 zeros and then 1, 0, 1, 1. Okay, if I calculate that, it will give us this logic. A and B in brackets, or brackets, A and not C, which is, a relatively simple piece of logic that we can actually use in the schematic later on. So as I've noted down here, it gives A and B, or open bracket, A and not C, which if I translate A, B, and C values into their original signals, then which it gives us this. It gives us open bracket, the reset, underscore reset, and or idata, close bracket, or with the result of reset and not, if not 0, signal, close bracket. So we know that we can construct relatively simply and easily the relevant TTL logic for representing this logic. The rest of the TTL structure is actually not that difficult. Building all of the registers and everything is not going to be too hard. It was just when you're trying to figure out truth table logic, sometimes it's better to make sure that you're actually doing something that you expect and to document it fully. So now we've gone through the rough documentation for the simple CPU. Let's look at the schematic. So I'm using the Proteus tool, which you can get from Lab Center Electronics. It's a fantastic tool. I've used it for many, many years. It costs a bit of money, but the amount of time that it saves me when I'm designing electronics is significant, and I really love using this tool. And they haven't paid me for saying that at all. I just tend to use this tool. So this schematic has a few different parts, but it's actually not that complicated. Down here in the bottom left, first of all, are some standard headers for accessing the standard expansion bus and video bus signals that I would normally expect to see from the video hardware. I just put these into my schematics and my design because eventually I want to connect this CPU to this these external memory buses, but to be honest, they're not connected up at the moment or anything. But basically, they look like this on the left-hand side of the circuit board. And if I go to the rendered view, then you can see if I spin it around, you can see what the connectors look like. They're the standard connectors that are on the rest of the video hardware. Let's close that. Let's also close that. I don't need that. Zooming back out again, up in the top left-hand corner here, we have basically a whole bunch of debugging and a simple clock generator here. So this is the clock generator. I'm using the simulation primitives here to generate a CPU clock, which has a frequency of 1 megahertz, and that goes into the CPU clock signal line here. And I've also got a reset signal here, which lasts for, well, it goes from low to high edge, which means it goes from low to high, and it does that at 200 nanoseconds into the simulation. I also have a simulation primitive here for a reset button, which drives the signal down to ground. This is so that as the simulation is running, I can trigger a reset back down to ground when I want to. So that's the clock generation. Over here is just some connectivity for a virtual logic analyzer, and I can show you this when the actual simulation starts running. But basically, I'm looking at the CPU data address signal, the internal data bus, which is the internal data value that's currently being selected, the value that's coming from the internal work RAM, and also the CPU program counter. I'm also logging in this logic analyzer the internal write RAM signal. And by convention, it is prefixed with an underscore, which means that it is write on low. Most of the RAMs, when you're talking about TTL, actually write values when you hold a signal low. And then when it transitions from low to high, that's when it stops trying to write the value that you are asserting on its data bus into memory. Over here, slightly on the right-hand side, we have a whole bunch of debugging values, and basically I've created some standalone buses with the relevant bus label names, and then I've attached a probe onto each of these so that when the simulation is running, I can see the value of the CPU's PC, I can see the value that's held inside the RAM data, I can see the value that's held inside data register A, B, and C. I can see the reset instruction signal. I can see what is the immediate value. I can see the CPU data address value, which is the register for the data, the address register, basically. I can see the output from the ALU, and I can also see the input data that's also being asserted on the input data bus, which is the internal data bus of the CPU. And over here, what I have is that I also have another simulation primitive, which is basically a data generator, or in this mode, it's actually set to record. So it records to an output file all of the memory address writes that are asserted by the iWrite RAM signal, and it records the RAM data bus, and it also includes the RAM data address that I want to be writing. So it records this to a nice file so that I can use this output file later on to validate the memory writes that I expect to see. Because we're running known code, we expect this code to have a known output, and we want to be able to validate that known output later on. So that is basically the debugging and how it's all set up in the simulation. Now what we have here is the start of the CPU proper. So what we have here are 3 ROMs. Each of these ROMs is being fed with the CPU program counter, and it's only the first 8 bits of the CPU program counter. Remember, I was going to have the program counter and the address register as all 8-bit values. The other address lines are being tied to ground, and obviously the ground is also being sent to the chip enable and the output enable. Again, the convention is that if it's got an underscore or a little horizontal line above the signal name or below the signal name, then the component will only output something if the input here is driven to ground. So that's why we drive it to ground. And you're enabling the chip here. CE is chip enable, OE is output enable. The VPP indicates that this is an EEPROM, but we're not actually programming the EEPROM. How we program, in inverted commas, the EEPROM in the simulation is that we actually give it the output binary file from the code that we want to load. And this output binary file comes from some assembly code which I assemble and then output to basically represent the pseudocode that I want to see. Okay. But basically the program code loads each of the outputs. Now, we're going to go to the real assembly code in a minute, and I'm going to show you what that looks like. But basically, each instruction for this simple CPU has about 24 bits, minus a few, minus 4, about 3 actually. But basically, we have 8 bits here for writing the register A, B, and C, and the address register and the program counter signal here and the RAM. Right, we also have the first 2 bits from data select, and we have the 3rd bit for the data select coming into the 2nd byte. So we have a second ROM here, and if you recall, I mentioned that the outputs from the ROM won't be stable, so we have some 8-bit latches on the CPU clock. Basically, the CPU clock is at 1 megahertz. And so we want to use the CPU clock for latching a stable output value from the program ROMs. Okay, and also during a reset signal, the MR, because it's low here, this little circle knobble thing here on the simulation primitive indicates that on low, the memory reset will reset the value held inside these 8-bit latches, these 74273s. These are very useful 8-bit latches. It will reset the value of those internally to 0 on a low reset value. So we latch the value here to get a stable value. Now, because we have a conditional instruction, what we want to do is that we want to use the output from the conditional instruction. We don't want to execute the instruction if the conditional instruction execution says that we don't want to execute the instruction. So this is why actually we have a second layer of 8-bit output latches here. Now, these output latches will be 2 cycles behind what the ROM is showing. But that's perfectly fine because as I'm going to show you in a minute, each pseudo instruction actually has around about 3 different states. Anyway, because this is a simple CPU, we're actually using, say, 3 states to represent a starting state, the edge of the state, and then the output state, because all of these signals here, the right signals, are going to latches eventually, and these latches will only latch the value, will remember the value on a positive edge, in other words, from low to high. The same as these latches here, they only remember the value that they see on the input when they see a low to high clock signal or a low to high digital signal on this input pin here, and also memory reset has to be high, obviously, otherwise it's going to be resetting itself all the time. But a low to high transition will remember the value on the input and present it to the outputs here. So ROM shows a value to this first latch, which latches it on the clock signal. And then the second clock signal, or clock signal plus 1 if you like, will then latch what it sees from the first latch. So this latch will be lagging behind a little bit. But that's useful because we want to do some calculation on whether or not to really ignore the instruction. And the way that we ignore the instruction is by resetting the instruction value here. Okay, so what are these signals and where do they come from? Well, these signals actually come from the program ROM, and the program ROM data comes from this pseudocode, which I'm going to show you now. Now, the pseudocode actually is just an assembly file, and I'm using one of my favorite assemblers, which is the Acme assembler. Now, the pseudocode actually pretty much starts here. The first commented line of the pseudocode is write address with the immediate value of 13. Now, I haven't written a full assembler. What I'm doing is that I'm using the macro ability of the Acme assembler to construct the internal state signals that go into the different program ROMs. Now, all of these signals are represented by these label names, and you'll notice that this bit pattern here counts up. So say, for example, write register A is the least significant bit here, and the least significant bit in the simulation is here, because this is the least significant byte, the middle byte, and the most significant byte, okay, of the instruction. And it gets piped through to here. So this is a single bit signal. I write reg A corresponds to I write reg A here, and I've used the same, pretty much the same signal names as I used inside this pseudocode. So what I'm doing is that I'm taking I write register, which is this signal here using this bit pattern here, ORing it together with select immediate. So I'm selecting the immediate value from the program ROM. Now, the selection, because I've got 8 things that I can select, I can actually use an 8 input to 1 output demultiplexer. Okay, so the demultiplexer takes 8 different inputs, and based on the selection of a value from 0 to 7, which is why we have 0 here, 1 here, 2 here, 3 here, 4, 7 here, represented by the binary 111. Okay, we have 8 different inputs going to 1 output in the CPU design, but basically this is a demultiplexer, a selector of data. I am selecting the immediate value, and by convention I've just given it the value of 0, the immediate value from the ROM. The next instruction looks like this. I am writing register A with the immediate value 0. So I'm writing register A with the immediate value of 0. And the next instruction is writing B with the immediate value of 1. I'm writing register B with the selected immediate value of 1. There is a loop label here, which signifies the start of the loop, which is the start of the loop that we saw here, which is in the pseudocode loop. And then the next instruction is the write RAM and write C with the result of adding A and B together. So what we can see here is that if we go back to the code, write RAM, write C with the result of adding A and B together. Looks a bit more complex, but basically all it does is OR together the various signals. Okay, so and the expected values for the register for the instruction. So the write RAM signal is asserted. Also, the write register C signal is asserted. And we select the ALU, the result of the add. And we tell the ALU that we want to select register A as input and register B as input. And we keep on going down the pseudocode here. So the write AB basically does a copy from register B to register A. Write BC copies from C to B, for example. Then what we do is that we increment the address register by 2. We're doing the same thing here, but this time we're using the ALU, we're using the output from the add to add to, which is an immediate value, and we select the immediate value in the second part of the ALU, and we add 2, which is the, by convention, but for this macro, 2 is the immediate value, which is going into the instruction ROM, and we select the input A of the ALU, the address register, and then we write back into the address register, and I'm selecting the output from the ALU calculation. I'm selecting the output from the add, and so on and so forth. So this code basically does what you would expect. The comparison instruction actually uses 2 states together because it's not, it would complicate the design to add 2 immediate values. So what we do is that we want to have 2 immediate values. The first immediate value is -89 for the comparison, and the second immediate value is the address for the program counter to load. So we don't want to have a complicated design. So what we do is that we split this instruction up into 2 different states. First is that we write into a temporary result bit latch, okay, the result of the ALU calculation of adding register A and the immediate value minus 89 together, and then we write the result for that. And then what we do then is that we do the if, and this result bit register, if you like, takes the result of ORing the output all together and telling us whether or not it is 0 or any other value. And then the second part is that if is the conditional instruction, which is the if not 0, the conditional instruction. Okay, if not 0, then write the PC with the result of the immediate value. So if not 0, write the PC register with the immediate value of the loop. Now I subtract the instruction offset here, and that's because the instruction offset is being passed into the start of the assembly here. And what I'm doing is that when I assemble the output by running this command line, I'm actually setting the program counter to be 0, 1, or 2 up here. And I'm using the program counter to basically tell the assembler to output either the first 8 bits, the second 8 bits, or the third 8 bits, basically the immediate value of the instruction. So that's why I know that the instruction is around about 24 bits wide. Well, it is 24 bits wide, because I know that I'm using, say, 12, rounding it up to the nearest byte. I'm using 16 bits to represent the internal states. I have 3 more bits available here, but I'm basically using 16 bits for the internal state registers, and then another 8 bits for the immediate value storage. So that's why the CPU uses 3 8-bit program ROMs, and that's why it's 24 bits wide in terms of each instruction state. Okay, now the instruction itself, the MI macro, can optionally take an immediate value. If there isn't an immediate value, then the immediate value is always 0. This is just a nice utility here in terms of macro. But basically what it does, what the assembler does, is that it is, what the assembler does is that it is taking the 3 state changes to represent a base state, and then introducing an edge, and then going back to the base state again. This allows me to easily create 3 different states to represent the instruction as it passes through the state that I want it to actually assert inside the schematic itself. You'll notice here that I'm using an I_held__mask variable. What this does is that basically I want to assert all of the ALU. Well, I want to assert which register or which data is output to the internal data bus. I want to hold that earlier in the instruction. I also want to hold the PC load logic low, because I'm using an internal counter earlier, because the internal counter needs to hold it low for a clock cycle before it basically remembers the inputs that are on its counter inputs. It doesn't quite operate the same as a latch, which is slightly annoying, but that's what the counters do. And I also want to maintain or to hold the state of which inputs I'm selecting for the ALU2 inputs, right? The input A and the input B. So I want to hold those or longer. All of the other signals to do with writing or loading values, I want to have those as an edge. That's why I don't have those as part of the held mask. Okay, so when the assembler outputs, all it does is basically it runs through, I'm running the command line here, same command line, I run it, and it tells me that it's outputting a number of bytes. And it's basically outputting those to the expected output files. So if I go to the output files here, then the 3 output files are here, here, and here. If I look at them in the hex editor, then these are the 3 output files. Blah, 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 blah. And those get loaded into the program ROM in this schematic. Now, these output signals, to be useful, some of them need to get inverted, because when this goes from, because I want to have an ignored, or I want to have the default state instruction, the nothing instruction, the no op instruction, because I want all of the bits to be 0, I want to invert some of these, because actually some of the latches will start to remember values when you go low to high. So I want to actually invert the transition, and basically this would be from a low to high, but I want to have the instruction latches start to remember their stuff when this is high, so I actually want to invert them and bring them down low. That's what this logic here does. Some of these signals, they're basically being inverted by NOT gates, and you'll notice that the input signal label is not prefixed with an underscore, and the output one is prefixed with an underscore, just by convention, just so that it helps to make things a lot easier to read. So this is the program ROM. What we also need to look at quickly is the program RAM. Now the program RAM is a little bit easier, kind of, because it's only a simple 8-bit piece of memory. The RAM data signals here, 8 bits, are input and output. And we have the CPU data address register represented here, which is also 8 bits. We have a signal here which on low writes memory rather than reads it. If it's high, then these outputs are going to be what is in the current RAM at this address. And the internal data bus, basically the value that is asserted or selected from the select logic for the internal data, is optionally, when the RAM is being written, is passed through. This is again the low chip enable, and the data direction here is set to be high. So high logic means from A to B. AB means A to B. So only when we are trying to write RAM, we take the data on the internal data bus and we pass it through and we present it to the RAM data internally. So what this means is that when the RAM is not being written to, we isolate the internal RAM data values from the internal data. So we're able to pull out that information separately if we want to. But when we're writing it, we want to pass through the data that we expect to see from the internal data bus to the RAM. We present it to the RAM. The RAM will then remember it only when this signal is being held low here. Okay, this is fairly standard memory logic. What you don't want to do is that you don't want to alter the address being passed in while you're holding the right signal to be low and stuff like that. You need to make sure that you read the data sheet for how these RAMs operate to be able to get good stable operation. And basically the states for the CPU, when it's doing a memory write, will hold the address hold the address value at its correct value first, and then in the middle of the state it will assert the correct logic level low on the RAM write, and then it will release that and set it back to high again before even considering to change the address here. So all of that logic is held internally with the address register, and how the state signals are propagated through to the RAM, for example, inside the CPU. So we all know that that's hopefully going to be okay. The next part of the design is up here in the top right-hand corner of the design. So these 4 latches here represent from top to bottom the address, registers A, B, and C, and down at the bottom we have the address register. They all use the same latches. They optionally latch the data that's held on the input data bus, and then they present it on their relevant outputs. All of these outputs are discrete signals. They don't conflict with each other. They're on separate buses, okay, because we select them later on, and I'll show you these selector in a minute. each of them have an independent signal for writing, and they also have an independent signal for resetting their currently held values. If we scroll down, we can see that all of these independent data buses are discrete. Okay, this is the CPU data address bus. And what we can actually show now is that we also have the CPU's program counter. Again, the CPU's program counter is reset with a low on the memory reset value here. And what we also have is that we have set the relevant signals for I want to count upwards, please. We are also, say, for example, setting the CPU clock, and we also have the write register PC signal, and again it has to be held low for a clock signal before this will remember the data that is presented on the input. If it's high, it basically ignores what is on the input here, and it just continuously counts up from its internal state. It actually remembers the values. Because these are 4 bits, they need to be chained together to produce an 8-bit output value here, which is the CPU PC bus, and we connect the two by connecting the carry here so that we correctly carry forward the result of the calculation. Okay, so whenever CPU clock goes from low to high, then it will either remember the input value, or mostly it will be counting upwards, 1 value for every CPU clock. Now, we were looking at the address registers and the general purpose registers and the program counter a little bit just now. And this down here are the 8 demultiplexers to basically demultiplex based on the iData select binary value from 0 to 7. It selects either 0 to 7 inputs here. Each input signal then results in an output signal. Now we have to do, because the internal buses are 8 bits wide, we have to have 8 of these all correctly labeled up to select the 8 bits for the internal buses 1, 2, 3, 4, 5, 6, 7, 8, 9. And we are looking at selecting the immediate value from the program run, the RAM data value, the data register A, B, and C, or the data address register, or the CPU program counter, or the ALU output. Okay, so if I right-click on here and I highlight the net on the current sheet, it will show us that data reg 0 comes from the output of register A, for example. It will show us, if I look at, that's the inputs, the ALU. If I go back here and show you the RAM data, seriously, I don't know why the behind neighbors have to start doing power tools work just as I'm trying to do this, but anyway, apologies for the noise in the background if you can hear it. Hopefully it's not too bad. So if I look at the RAM data path here, I can highlight the net on the current sheet, and I can see all the way down here that it knows that the RAM data comes from the RAM, but it can also come from the output of the write address bus, if you like here. So I know that the RAM data is all connected up. And this basically allows me to select any of the 8-bit data values coming from the various different places. Now, when we talk about the ALU logic is here, this part of the schematic. The ALU just basically presents an add operation. Now, the add operation is just two basic basically two 4-bit adders chained together as you would normally expect, which is perfectly fine. The 4-bit adders are chained together with a carry in the middle, again as you would normally expect, and the input carry for the first adder is brought down to ground. Now these adders are 2's complement adders, so if we present a negative 2's complement value here or here, then it will just do a subtract rather than add. Hence the magic of 2's complement binary arithmetic, which is brilliant. Anyway, so these two adders here have two different separate 4-bit inputs, and these 4-bit inputs here and here, if I can select them, thank you very much, these two separate 4-bit inputs actually come from two pairs of demultiplexers. Remember the definition for the ALU inputs allows me to select two different values depending on if it's input A or input B. Remember that from the initial design. So here what we have is that we have the selector signal, and if I highlight that on the current sheet, then the selector signal comes back from the program ROMs as you would normally expect. Okay, highlighted here in red. The output signal here either selects on low A or high it selects B. And what we have is the input for register A or the input for the address register. So register A or the address register is demultiplexed and then fed into the first ALU input here, and the second ALU input, which is down here, second ALU input comes from this demultiplexer, which operates in roughly the same way, but this one basically demultiplexes the data reg B, the register B, or the immediate data value, which comes again from the program ROM, or the register B, which comes from the register B latch, which is all the way up there in the top right-hand corner, register B latch. So that's basically pretty much the entire CPU, apart from the condition and instruction execution. And this comes in two parts. The first part is the part which remembers the single bit of the OR I data value. If you recall, the OR I data value is represented in the truth table here. Now this OR I data value is as a reminder, basically remembers on demand, on request, when we want to write the result bit latch. It remembers the result of whether or not the current internal data value is 0 or not 0. And this is output to this signal here. Now the second part of the conditional instruction execution is over here. So we take the whether or not the last remembered result is 0 or not 0, and if we have the if not 0 instruction set, okay, then we pass it through the not, we pass it through an AND along with the reset, and again we build up here. This is an OR gate. Okay, this OR gate basically represents the OR that we saw in the output, the truth table here. It's this middle OR here. Okay, the bottom part is reset and not with if not 0, which is what we see here, and not if not 0 with the reset signal coming in here. And the top one is basically just an AND of reset of OR I data, which is the same as what we saw here. The reset and the OR I data, reset and OR I data. So this line here from the truth table solver is represented just by this part of the schematic here. And then this reset instruction comes down, and if I highlight the net on the current sheet, then the reset instruction is used to force the currently executed instruction state to either be 0 or to allow the current instruction state to be executed. And that's basically the whole CPU. Now, how do we know it's going to work? Well, that's a really good question. So what we do is we output and we inspect, and we can validate it using visual inspection, but we can also validate it using some data validation tools that I'm going to show you in a minute. So if I start executing this, now this will start the execution. Now I'm going to hide these temporarily. So what we have here is that we have the logic analyzer window. I'm going to hide that down there a little bit. We have the memory contents of the RAM, and we're only looking at the first 256 plus 16 bytes of the RAM. Okay. We can see the simulation log here, which tells us if we're doing anything badly timed with the memory or anything like that. Hopefully we won't be, because we're running at 1 megahertz. There shouldn't be any memory timing issues at all. Okay. But basically what we can do is that it's paused, and every time I click, it advances 200 nanoseconds, roughly. Okay, so the reset instruction has gone from low to high here. We can see that. I'll start it again. So initially, the reset instruction is low. That means that all of the reset instruction plus all of the reset signals are low here. The reset signal here is low. All of this stuff is being reset to 0 internally. Everything is being reset to 0 because the reset here is low. Now, if we inspect these registers, if I click, note what happens to CPU PC. Every few clicks, and I've set this up so that, say, for example, 3 clicks, advances the CPU program counter by 1. Then, as I continuously click, we can start seeing the immediate data being presented, and the first value for the immediate data is D. If we look at the hex dump, for the third one here, we can see that the immediate value of D starts to come through in the data, and that's because our first instruction presents the value 13, which in hex is D, as the immediate value for the address write instruction. Okay, so we know that we have started getting instruction data. And what we would want to see eventually, if I keep on clicking through and advancing the CPU PC, what we should see is that the data address register here should contain the value of D, which is 13. If I click once more and a few more times, there we go. The debug value of the address register has changed to 13. And then the program counter is 4, and so on and so forth. So what we can do is that I can just let this run now. I've already debugged this, so I know that it works. But basically, if I run it by pressing F12, I can see eventually that after there's some stuff and internal data updates here, and the data registers hold their end of program values, of course, as you would normally expect. I can see that the program counter here is basically going around in an infinite loop, which is the infinite loop that we saw at the end of the code here. So we're doing an infinite loop here, right here. And that's what we're expecting to see. But if I pause the execution, the memory window comes up. And the memory window is showing kind of what we expect to see in terms of program execution. So we're expecting to see 1, 2, 3, 5, 8, D, 15, 22, 37, 59, and 90 in hex, all separated by 0 values. These 0 values don't get written. And this is just basically showing us that we are writing a value, incrementing the address register by 2, writing the next value, incrementing it by 2, writing the next value, and we're doing it for the expected number of iterations in the loop. I think. Now, we can, when we're debugging this, we can validate it by eye, and we can have a look But sometimes it's easy to see, it's easy to miss that there are updated values and that they are the correct ones. So actually what I tend to do is that I tend to have a test case. Now this is using my 6502 BDD Cucumber based testing framework, but I've written some data file validation, so I can actually have a look at, because don't forget that we're using the data recorder, data generator in recorder mode, we're using that to record to an output file. So if I have a look at the data in the output file, we can see that we are getting expected results. So we're seeing that the value 1 is being written to address D. Value 2 is being written to address F, and so on and so forth. But again, it's quite easy to make a mistake when validating this by eye. It would be better if we can use some automated validation. And this is what this test scenario does. It's just basically describing the steps I would do manually, but it describes it in a way that the Cucumber framework behind the scenes can actually execute the test case and then make sure that everything is working. So if I run this by running the file, it should come up with green in a minute to indicate that the test scenario is perfectly fine. Now here is a comment saying I expect 1 to be written to address 13, expect 2 to be written to address 15, so on and so forth. And that's what I expect, and that's what this is validated here. So I know that the CPU has at least behaved in accordance with my expectations for how it should work. So that's what we get. I can clear the results now, because I know that the test case has executed correctly. So basically that validates the CPU execution. What I can also do is that I can use the Proteus tools to validate the execution using the logic analyzer. The logic analyzer is very useful if I want to debug certain states and see what happened in the past and see what happened in the future in inverted commas. So if I set up, well, first of all, if I set this running, it's going and running in its endless loop. Okay, but what I can do is that address A0, the input for A0 on the logic analyzer is, don't forget, writing to memory. So on a negative edge from positive to negative, or for if I have a logic level held at 0, okay, I can set this up to capture. Now it's on a trigger, capture trigger, and there is no memory writing going on at the moment. And that's because we're going around in this endless loop at the end of the program. But what I've done is that I've got a little reset button here. If I press the reset button, it will reset the CPU, it will reset the program counter back to 0, and it should run the same code again. And then it should trigger some memory writes, and we should see the memory writes inside the logic analyzer. And as if by magic, the capture light has gone off, indicating that the trigger condition has been met. And we can see here that a trigger condition has been met and accepted and actually logged in the logic analyzer. If I zoom out, you can see that there's a memory write here, there's a memory write there. I can scroll along here, and I can see that there are several memory writes, as you would normally expect. If I zoom in, we can look at all of the signals that have also been captured. So when the memory was being written during this period here, I can see, for example, that B0, which is CPU address, is D, which is 13. I can see that the internal data bus, which is B1 here, is value 1. I can see that the RAM data currently holds the value of 1 because I'm asserting it from the internal data bus. Okay, and I'm presenting it to the RAM, so I want it to be 1. It also contains 1 because that's the value that's held in the RAM from the previous execution just before the reset. And I can see that the CPU program counter at that particular time when it was trying to do the write was at program counter C. The initial state here is B, C, and D, and the middle state is holding the address signal, the write signal low here. and it's holding it low for 1 microsecond, which is what we expect because we're actually running at 1 megahertz. So we can use the logic analyzer to see and to debug, and we can add extra logic analyzers, and we can record the outputs here, and we can inspect, and we can use all to debug. And this is why this simulation software is fantastic, because it allows you to build the schematic, but also to simulate it and to debug it. We can also have, say, for example, debug breakpoint values on these probe values here. So if I want to break the execution at a particular point and then single step, I also can do that too, which is fantastic. The great thing about this Proteus tool is that I can also do the circuit layout. So I tend to cheat at this point, and I tend to use the autoplacer. So what I'm going to do is I'm going to run through and run a quick autoplace here. The autoplacer does take some time. For some strange reason, the autoplacer thinks that autoplacing all of these components is a hard thing to do. The circuit board is quite small. I've hopefully made it the correct minimum size to accommodate all of the components. Most of the components are also actually using the IC component packages with the externally integrated decoupling capacitors as well, which I have used on the video hardware. This means that this design would effectively be good to go after it does its autoplace, and it is currently almost halfway through the autoplace. It shouldn't take too much longer. Once it's finished its autoplace, then and then doing an auto route, this design basically is then good enough to actually go and send off to someone like PCBWay to actually build. There is a little bit of manual effort that is needed to create the output book of materials and stuff like that. I mean, the book of materials output generation here from the Proteus tool is usually good enough to give to PCBWay, but sometimes there are components and stuff like that that you need to manually tweak to make sure that PCBWay buy the correct component or use the correct package, or whatever. So anyway, generally speaking, this tool is a complete end-to-end schematic design tool, plus also layout design and auto routing if you like. But you can do it manually. You can do manual routing as well, but I have pretty much always consistently used the auto router because I don't want to spend a huge amount of time doing manual routing for everything. Some people really like doing manual routing. I don't like it at all. So I cheat. It's not really cheating to use the tool for what it's meant to, I don't think. It's like saying that using an optimizing assembler is cheating, or an optimizing compiler is cheating. It's not. It's using the best tools for the job, rather than trying to maintain a whole bunch of stuff with human effort. It's just not efficient, and it's not cost effective, in my view. And there we go. It's auto-placed 39 out of 39 components. And now if I click the auto router, here we go, begin routing. The auto router is actually, comparatively, compared to the placement, really very quick, especially since I'm using a 6-layer board. It tends to be quite easy to auto route with the 6-layer board, even though there are 3 power planes. It does a really good job. So here we go. The power planes actually help with the routing because you don't have all of the routing for the power lines intermixed with all of the signals, which is good. There are 270 conflicts now. The conflicts should reduce to 0 as the routing goes on. 157 conflicts. The little yellow dots, the little yellow circles that you can see here, they represent conflicts. In other words, the signal density at the moment is a little bit dense around these areas, and it is having to do some extra work to resolve those conflicts. But it's gradually resolving them, and the way it does that is by adding a whole bunch of extra vias and hopping signals over each of them. As you can see now, it's going through the cleaning pass because there are 0 conflicts left. These are not conflicts, these are fires, because they're not bright yellow, they're darker color. It's doing a second cleanup pass. It's doing some optimization passes. But basically, that's almost at the end of this demonstration and this tutorial of how to get from pseudocode to TTL schematic, how to validate the schematic in execution, and then how to get to a board which can be fabricated at the end of the day. So it's finished the routing. If I zoom in, there we go, it's patched up all of the holes and everything. It's tidying up everything now. But basically, if I zoom in, you can start to see all of the signals going around everywhere. It looks really quite nice if I zoom out. And if I go to the 3D view, this is what it looks like in the 3D view from the top view. Once it's finished rendering everything, it hasn't quite done that yet. Here we go. It's going through. There we go. The silk screen and everything is done. There you go. I can look at the back. Looks really quite nice. You can also flip it using a little control here, but I tend to spin it around as well because it looks quite nice spinning it around. You can look at the different sides, top, bottom, side view. You can zoom in. You can see what it looks like. You can check all of the signals, and you can. What this is really good for is that you can take this rendered output. You can take it as a screen. You can screen grab it, and you can send it to your PCB fabricator and assembler, like PCBWay or SceneWay. I use both, and they both produce working boards generally, although my other YouTube videos sometimes show that they need a little bit of fix-up. Generally they produce working boards. And you can send these pictures to PCBWay, and you can say, look, this is what it's meant to look like when it's assembled. This is the orientation for the connectors. These are the placement for the ICs and stuff. This is what it should all look like when you've assembled it. Please, try to follow these rendered outputs first. You can see that it's on the top of the board. I want them on top of the board, not on the bottom. So on and so forth. Right, so a picture paints 1,000 words, and this is a very good way of getting to an output PCB. And that is pretty much the end of the end-to-end example of how to get to start using TTL electronics for a very simple CPU. Now, there are some things to note, and I've noted those things to note down here in the document. So the first thing to note is that the limiting factor for this design is basically going to be the access time for the instruction 2732 ROMs. Currently, the ROMs are configured with the address access time of 200 nanoseconds, which equates to a theoretical maximum of 5 megahertz, because the clock rate of 5 megahertz gives you 200 nanosecond pulses. And basically, that is going to be the theoretical maximum here. We're running it at 1 megahertz, so we're not encountering any issues. This is the address access time for the ROMs. If I reduce this, of course, then that means that we can run at a faster rate. But this is great because actually it shows that the simulation will show that the design fails when you crank it up to, say, 5 megahertz. So if I put it to 4 megahertz, theoretically that should be fine, right? So 4 megahertz, excuse me, 4 megahertz, if I let it run, and then I do a quick visual inspection of the memory, it seems that everything is correct. And if I do a real validation of the output data, the real validation of the output data also shows that everything is green and fine. That's cool. However, if I crank it up to the theoretical failure point, which is at 5 megahertz, now the simulation, of course, introduces some extra random or pseudo-random latency to all of these signals. It introduces this because it wants to help you produce a much more robust simulated design. So the latency is by default, okay, and I haven't changed the default value. So if I crank it up to 5 megahertz, I would expect to see this initially start to fail. So let's see what we get. The program counter is kind of looping through its thing at 1B, 1D, whatever. But we can see if I pause it, it's only written the first two memory addresses and then it's failed. Now I can debug this a little bit further and find out the exact point of failure, but basically it's going to fall back down to the signals in the ROM being a little bit too slow. So basically, after 200 nanoseconds, the signals are not guaranteed to come through correctly. Okay, and if I run the validation here again, run the file validation, it will basically come up and it will say, the first two memory writes were fine. The third memory write has come up in red on the step line, and that indicates that the data file is bad. Let's just double check that. The data file output is bad. It hasn't done any other write attempts after the first two writes. This is perfectly acceptable and it's a perfectly expected failure because we're cranking up the clock rate to be far too fast. The other things to note, before I forget, the program ROMs and internal data RAM are quite small. It would benefit the design to make them larger and convert some or all of the program address space to RAM. This is if I was going to use this as a more of a general purpose CPU board as opposed to just a quick demonstration. Of course, there's always the ability to add onto the PCB a clock crystal or oscillator and also clock divider logic to allow you to divide down the clock that you want to pass in. I could also add read and write support for the external 24-bit address bus and also the external data bus. The CPU would then be able to drive the audio and video hardware in standalone mode without needing a Commodore 64 to drive the video hardware. This basically makes it a self-contained computer. A self-contained computer would, of course, need more ALU operations, and I've got some bits free which could represent the different ALU operations anyway, so that's fine. And, of course, I can just expand the instruction bit size anyway, which is not really an issue. I could add more conditional execution options, not just, if not zero. Typically, in a CPU like this, you would have a status register, and it would have status not equal or equal. It would have a carry, set or clear bit. It would have an overflow bit. It would have, a negative bit, for example, and stuff like that. You could do conditional execution based on these different execution bits, if you like. I would need some I/O support, maybe a 9-pin D-sub connector for joystick, and also a PS2 connector for keyboard. This is if I wanted to progress the design to be a standalone CPU board. And then, of course, to integrate very well with the video and audio hardware, or video hardware specifically, because I've got access to the horizontal and vertical count values anyway from the bus connectors, from the backplane connectors, basically, I could add a CPU pause and resume execution or trigger on various input video HV values, basically producing the same kind of functionality that the APU, the copper blitter replacement board does. Now, the APU board is massively complicated compared to this simple CPU. That's why I did this demonstration, was to show a simpler CPU being built from scratch, rather than looking at the design for the whole huge, complicated APU. And that brings us, I think, to the end of this demonstration. I've tried to keep it to be less than an hour and a half, and it's an hour and a quarter. So that's pretty good. Thank you for watching up until this point. If you like what I do, then please like and subscribe this video. It helps to give me feedback on what things you find interesting, and then hopefully I'll produce more content on the things that you will find most interesting. So thanks again. Take care and have a great day.